we'll just start recording here. I'm recording now. I'll take this and I'll upload it later on and notify everybody of this. So we won't have a live stream here, but that's okay because usually, at least for the Omaha section, not many people are watching the actual live stream. Anyway, we started off with stacks, or we finished off with stacks last time, and then we started in on queues. And queues are basically, well, as the name suggests, they're lines, right? Just like the British term for a line, where I have, a queue usually is depicted as this horizontal line here, and things go in one end. We call that end queuing, right? And queue. Excuse me, and then things come out the other end, and I'm going to call that dequeuing, right, or DQ, okay? Unfortunately, a lot of implementations will use the same terminology, push pop, or other terminology like offer and pull, and we'll cover those here in a second, but otherwise, I like to use NQ and DQ. Why? Because the data structure itself is called a queue, right? And so I like to use terminology that is relevant to the name of the data structure here. So if things go in one end, right? Here's Jordan again, right? If things go in one end, then they come out the other end. And so consequently, a queue is a first in, first out data structure, a FIFO, right? Or first in, first out data structure. And it's still a restricted access data structure. You're only allowed to put things in one end and take them out the other, at least conceptually, because if you want arbitrary operations, then you want a different data structure. So let's come over here to Eclipse. And remember that we've got this myStack implementation here. I'm going to go ahead and create another implementation for a queue. Right? Now, I don't know whether or not we did it. I'll call it myQueue. Right? Queue. There we go. And I don't know whether or not I demonstrated this last time, but what if we were to, say, not use the way that we did it last time was we used a composition here. What if we were not to do that? What if instead we were to actually use inheritance for this? Extends a list data structure. Right? Does that sound right? So is a queue a list? Well, what's a list? A list is something that you can arbitrarily do anything you want with it. You can put anything anywhere, you can access anything anywhere, you can replace anything anywhere. Does that sound like a queue to you? No. Nope. So what if I went with the reversal? What is a list a queue? Not really, no. Right? So here is an instance where composition is preferred over inheritance, right? What we're going to do is we're going to take this list data structure, and I'm going to use the same linked list over here, and I'm going to put it into my queue. Right? Now, the two operations of public t dequeue, right? Remove an element from the front of the queue, and public void nq, right? T element x. Right? Now those are going to be my only operations, right? And similar to the stack, of course, I could do other things. For example, I could peek at it, right? I could have this is empty. In fact, I could just go ahead and grab that and copy it because it's going to be exactly the same. And it's not the stack, it's going to be, I'll just call it the elements. Right, there we go. Elements, there we go. I do need to be careful here though. If this is a linked list implementation, then I need to make sure that if I'm working from one end, then I'm doing the other operation from the other end. So as long as you're, as long as you're consistent about it, it doesn't matter which end is which. Right? So what I'll do is I'll say, if to dequeue this, I'll say elements dot remove the element at index 0. So in other words, visually my index over here, the index is going to be 0 over here. And so the index of size -1, that's where I'm going to dequeue it. Right? or sorry, I've dequeued it from one end, and so I need to enqueue it at the other end. Elements dot add x. There we go. Now remember, the default behavior of add here is going to be that it appends to the specified element to the end of the list, which is what I want, because I'm going to be removing it from the front of the list and returning it. There. So let's take a look at this demo here. And instead of a stack, what I'm going to do is I'm going to do a queue. Queue. There we go. My queue, my queue. And instead of push here, I'm going to go ahead and say enqueue on all this. Come on. Enqueue. There we go. And instead of pop, I called it dequeue. There. So if I'm putting in 10, 20, 30, or 40, and I dequeue, 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 first in, first out, 10, 20, 30, 40, that's going to be the order that they come out in. Right? Just the opposite of a stack. Right? So very, very subtle difference here between a LIFO and a FIFO. Okay? Not that much, right? Once we did one, then we basically did the other. All the other operations, right? Like a peek operation, you can return but do not remove the element at the top. What happens when you not pop but dequeue from an empty queue, right? Do you impose a capacity? How do you implement a queue? Well, we're implementing it with a linked list data structure here, right? So those two operations that we just implemented were enqueue. Enqueue is insert something at the end of the line, right, or the queue, and dequeue, right, remove something, remove the element at the front of the line. Right? Front of the line, end of the line, right, get back to the end of the line when somebody is trying to cut, right, that's why we call it the back of the line. Get into the back of the line and wait your turn. Right? So there are queues, right? There are, of course, variations on that, right? The variations are actually much more interesting than the queue itself, right? For example, you could support the arbitrary removal of elements. Right? Why would you want to do that?
Inside of a queue?
Yeah.
I feel like that kind of defeats the purpose.
Well, maybe not. Right? What if you get in a really long line to go on a ride, and you get tired of waiting? You time out and you leave, right? That could be a data structure that you want to simulate, right? There's a timeout, and so we're going to go ahead and just leave, right? Or maybe, nope, that's no longer relevant. Whatever request that was that represents, right? It's dead because the person is no longer logged in or something, so it leaves the line, right? You could, of course, wait until it gets to the front of the line, then ask the question, is this relevant anymore? No, okay, then ignore it, right? But it's still waiting in the queue, right? So you could, line levers, right? Line levers, right? If you want to simulate something like that. You could allow arbitrary insertions. Right? Why would you want to think, now again, think in terms of lines here. Why would you want to maybe do that?
Something needed priority.
Yeah, priority, right? In fact, that's exactly the term that we use. I was going to say VIPs, right? Very important people, right? They no, they go to the front of the line, sir, right? Because they paid more or something or whatever, right?
Wouldn't they be within a separate queue?
Maybe line jumpers, right? It really depends, right? For example, the classic example that I give is nice, right? And nice. Yep, there we go. Let me bring this over here. So there's a nice utility. You execute a utility with an altered schedule priority. So think about an operating system. An operating system or a system itself, right? There are thousands or hundreds or thousands of operations that are running at any one time. Here's my computer right now. Oops. Nope, I just have top. Yeah, there we go. Here's my computer right now. There's OBS at the top taking 130% of my CPU despite the fact that it claims it's only 7.7. I knew it was lying, right?
Okay, hold on, what is that thing?
OBS, that's how I'm streaming. I'm not streaming right now because it's a recording.
The-
Oh, this is this utility. This is top. Windows users would recognize it as Task Manager or whatever, right? And so all this is all the things that are running on my computer at any one time. Who gets next, right? Everybody gets put into a line, and the operating system says, okay, you can go ahead and execute for a few nanoseconds or milliseconds or something like that. I'm going to put you to sleep and let somebody else take over because we only have, well, 8 processors here with hyperthreading, maybe 16, and you know, there's priority here. Generally, system level stuff gets higher priority, but what you can do is you can alter that by using nice, right? I will be super nice and let everybody go ahead of me, right? So if you're standing in the line, no, go ahead. I'm not that important. Just go ahead. Go ahead of me. And I believe that n it's like a level between 1 and 20. Or no, the priority can be adjusted over the range -20 to the 20. So the lowest priority here is going to be 20. The highest priority is going to be -20. So no, I need to execute here. So I'm going to shove everybody out of my way and jump to the head of the line, right? And this is a way that you can actually change that. So otherwise, if everybody has an equal niceness, right, then everybody is served just like a regular queue. But otherwise, this is going to be a priority queue depending on the niceness that you want to execute, right? So you could allow VIPs, you could allow line jumpers, people shoving each other out of the way to get to the head of the line, right? That's what's called a priority queue, right? So that's a priority queue allows you to define priorities for each element, right? And the next one that gets served or you dequeued, right, is the one with the highest priority, right? So how would you go about implementing that, by the way? So here we've just got a regular old queue, right? My queue. And I'm just putting things in at one end, I'm putting things in, and I'm taking them out at the other end, right? So instead of enqueuing it just at the end every single time, what would I do? If it's a priority queue, right? I would search for where X belongs based on its priority and insert it there. Right? So I'd start at the end of the line, right? And I'd say, all right, is this person, do you have a higher priority than this person? Yes, then we go forward. Do you have a higher priority? Yes, then we go forward. Do you have a higher priority? No. Okay, that's where you belong, between these two people right here. We're standing in line. And that's going to be what's called a priority queue, okay? There's actually a much better implementation of it that we'll talk about later with a heap, but we're not there yet because we haven't introduced trees.
Would you want to make, you know, whatever T is, actually have like 2 parameters then? Like
Yeah.
the data and then its priority number?
Yeah, you could say have and the way that I would do that generally is going to be here. I don't want to mess this class up, so let's go ahead and cut and paste this and call it my priority queue. There we go. So what you would do, what I would do, and I think that this is in lab 15, is if you were to do this manually, what I'm going to do is I'm going to have a map of elements from T to an integer that represents their priority. Right? Priorities. And then you give me an element and int priority number or something like that. And then I would, of course, search through and add it where it belongs, but then also I would keep track of its priority so that I didn't have to, you know, store it within that class itself there. Instead, I'm storing it in this map. Come on. Okay. It is equal to new hash map. There we go. Bring that in. Bring that in. And then I would also, you know, I'm not going to do it, but this dot priorities dot add x priority number. There. Just keep, or not add, but put. That's what I would do. Now, A little bit better implementation would be, don't have this map at all, instead have a, I need to ask, here's X and here's Y. Does this have a higher priority than that or not? I've got two things that I'm comparing. So what kind of thing would I bring in? A comparator. And then that's where I would put the logic. Here's this thing, which one has a higher priority, right? For, you know, CMP, whatever. Comparator for elements of the same type that you're holding here, right? That's what I would do. Get rid of that. Oh, what's wrong now? I broke it. Oh, I was making all these changes to my queue instead. Darn it. All right, roll back. Sorry. There. And then roll this back too. Oopsie. There, we're still good. Okay. All right, so that's a priority queue. You could also work from both ends. A more general data structure that can simulate both a stack and a queue is a deck. Right? And this is pronounced deck, right? It's not DQ or whatever like that. It's deck, right? And basically, it's a double-ended queue, right? Basically, you can insert and remove from both ends. So how can you simulate a stack? Well, you just work at one end and you ignore the other end. How can you simulate a queue? You work at one end for insertion and at the other end for removal. But how could you bring to bear the fact that you can work at both ends? Right? So for that, let's go ahead and go over here to look at this as a, let's say, operations. Let me go ahead and draw it vertically like this. Right. So suppose that you could do 3 operations. You could insert here, right? And then you could also remove, right? So push and pop at the same time. Now, if you just close it off, then that's just a regular old stack. But what if you don't close it off? What if you can also remove elements down here? Right?
Suppose then rather than a stack of plates, you just have like.
Yeah, something like that. Yeah. What kind of a use case could you come up with here? So now think about a typical text edit. Say what?
For dumping a stack. Maybe?
Okay, yeah. So, for example, there are 10 things in here. There's a capacity, right? Now, something down here, you put something on the top, and now there's 101 things here, right? But that's too many. So which one do you drop? The bottom one. Now, here's a great example of a use case. Open up Word. Start type. Oops, I didn't mean to do that. Undo. Operation. Undo. Right? That's a reversal. That is a stack. Right? Here's operation 1. Here's operation 2, operation 3, operation 4. If you go undo, right, it goes in the reverse order that you did it in. But you don't have a lot of memory to work with, right? Because actually keeping track of what the operation does and what it did, right? That takes a lot of memory. And so what we're going to do is we're going to say, oh, no, you can only undo the last 10 operations. Right? So 5, ... up to 10. Now, the 11th operation here. Right? We don't want to lose our breadcrumbs, but we don't want to also, have too much memory here. So what we're going to do is we're going to take this last one and we're going to eject it so that we're only keeping track of the last 10 things that you did. We're keeping the memory footprint low, but we're also enabling you to do and undo and redo, right? So there's one application of this, right? So application, keeping track of operations and undoing them, but limiting the number, right? And ejecting the oldest one. You're doing some system stuff right now. Have you talked about caches? What is a memory cache? Oops, sorry.
I don't believe so.
No? Okay.
We talked about queue and stack.
You have, okay. An LRU is a least recently used cache, right? So the memory of a computer, right? You've got very, very fast memory on the chip itself, right? But that's expensive because that's the fastest memory. And so you go out to RAM. RAM is a little bit cheaper. That's a little bit, but it's still expensive, but it's also a little bit slower. Then you go out to virtual memory, which is on your disk. And so if the processor is needing a chunk of memory that's stored directly on there, right, then it's called a hit, right? That you're able to load that up almost instantaneously. If it does not on the chip's memory, then it has to go to secondary memory, which is going to be the RAM, and it's going to have to load it up. If it's not in RAM, it has to go out to disk to load that up. Each one of those things is slower and slower and slower, right? But of course, down here, hard drive memory, cheap, super, super cheap, right? But so how do you come up with a scheme for making sure that the hits versus the misses? A miss is when it's not loaded up into that memory module, and so you need to load it up from the lower module. And so how do you come up with a scheme that minimizes the number of misses and maximizes the number of hits? What you do is you eject you need to load something up. Something's got to be pushed out. And so what do? The least recently used one, right? Because nobody's used this in a while, so we kick it out, right? And that's what LRU stands for. And you can do it by, well, this one's the least recently used, so we'll go ahead and kick it out or something. There's another way. What's the other one? Undo features. I forget. So this was removing at the other end. I guess what's the other use case for the other possibility here? If we want to say insert and remove from both ends, but also insert over here. Right. There's our line jumper, except that it's a very specific kind of line jumper that jumps to the front of the line only, right? Butts in all the way to the front and gets their priority. Not very nice, right? Okay. In practice, don't write any of your own, right? Instead, in Java, you're going to have all these things written for you. Don't create your own, right? Generally, you use what is provided by the language or library, right? So in Java, our go-to here is going to be, guess what? A deck, right? So let's come over here to Java and get rid of everything that I did. Not all the stuff, the demonstration that I did, but let's go ahead and get rid of everything except for a deck, integer, right? D, right, is equal to new. Now deck, I believe, is just let's go ahead and leave it like this for now, a null. And let's go ahead and bring it in so that we can actually read the documentation. It is an interface, right? So a deck is not actually something that you can implement. Instead, you need to look up what the implementing classes are. What are your options for doing a deck? So here's Java deck. Let's look that up. Better Java docs over here. There we go. There's the deck. All right. And what are its implementing classes? Well, there's an array deck. Guess what that's based on? An array list. Right? There is a linked list. Guess what that's based on? It's a linked list. So let's just go ahead and go with a linked list for now, because that's what we've been doing so far. New linked list. Now, if you want to treat it like a stack, oops. Sorry, there we go. And let's go ahead and bring this in. And it's not parameterized, it's integer. I'll just leave it like this. There we go. Right? Now, this is just D. What do I have available to me? I can do a lot of stuff, right? I can say peek. I can peek at the first. I can peek at the last. In other words, I can work at both ends, right? I can offer at the beginning. I can offer at the last. So let's just read the documentation over here. Why do I need so many options? remember that we had a lot of options that we identified with respect to our implementation. What happens when you try to pop from an empty stack? What happens when you try to push onto a full stack that has a capacity, right? So here is an entire grid of every single one of these possible options. If you want to if you want it to throw an exception, you would use one of these methods: add first, remove first, get first. If you want it to return a special value instead, for example, null, right? You would use offer first, pull first, or peek first. If you want to work from the other end, take first and just replace it with last, and cut and paste all of those here. Right? If you want to treat it as a queue, right, then add last. There's the equivalent deck method. If you want to offer, in other words, you want to put it at the end of the list, then you would offer last, right? Remove, pull instead of DQ, right? And peek here, element, right? So basically, a deck allows you to do whatever you want. You can treat it like a stack, you can treat it like a queue, you can do anything, right? Let's go ahead and treat it like a queue. And so I will say queue dot add first, right? 10, 20, 30, 40. There we go. And then system.out.println q dot what is it? Pull for last. You just have to work at the other end, right? There. So 10, 20, 30, 40, 10, 20, 30, 40. If you want to treat it like a stack, you can do that as well. All you have to do is be consistent about it. I'll go ahead and add it first, add it first, add first, add first, or better yet, push, right? Because that's what it's called, push, push, push. And then my stack dot pop. No need for separate, distinct implementations. You just have one interface to take care of all this for you. Right? What happens if I do one more, by the way? Let's find out. There's an exception. What if you did not want it to throw an exception? Pop, remove first. The remove first that does not throw an exception would be pull first. So dot pull first. Why do we call it pull, by the way?
Would you like sample to see whether it's able to do it?
Yeah, you're pulling next. Like think of the line not as like a physical line, but think of going to somewhere and you take a number, right? And now we're serving 35. 35, 35. You're pulling the room. Who's next, right? And this will return a special value called null. So one nice interface that gives you all these options. You just have to read the documentation and treat it like what you want. Cool. Exactly. Okay, so what are some applications of these things? Where have you seen stacks before? Program stacks?
Use to store return address.
Exactly. Call stacks, program stacks, right? Why? Because it's breadcrumbs, right? Storing breadcrumbs. There we go. So you go to a website, look up at the top sometime. You'll see, for example, let's go to ECE's website, UNL. There we go. So I want to know all about, advising. You'll note here that I did post about advising, like I went down there and got the advising sheet for what computer science 3 you should be taking because there was a question on that. And they suggest that you take it in your junior year. So don't ask me, talk to an advisor. Anyway, what are these things up here? Nebraska, College of Engineering, Electrical Engineering, and then we are looking at graduate degree programs right here. These are called breadcrumbs. In fact, if you looked at the actual HTML code for this, it probably call them breadcrumbs. How did I get here? Well, you started at this website, you went down to this sub-website, you went down to this sub-page, and then now finally you're at this page. How do I get back to where I came from? Well, you can go ahead and hit the back button like normal people, or you can hit the, click on this and go back up one, and then back up one, now we've lost our breadcrumbs here, right? But that's Hansel and Gretel, right? It's storing where you came from. Right? Hansel and Gretel, we all know that story, right? Right,
Well,
well, yeah, it did. They killed the witch, right? That ends well. All right. There are some graph algorithms, for example, depth first search that we'll take a look at later on, where you've got a graph that you're traversing, and you're walking through the graph like a maze. How do you know where you came from? How do you know that you've explored that corridor before? You need to keep track of these things. And the way that you keep track of them is through a stack, in your breadcrumbs. You can use it to simulate recursion. And that kind of makes sense because what is recursion? Function calls function calls function. It's just a call stack. Instead of abusing that poor little call stack that's only 4 megabytes, create your own stack that can be gigabytes. Right? And now you simulate that recursion by keeping track of what you've done so far.
where's that stats?
Say what?
Where's that stored in?
And remember, the heap. The heap, yeah. Instead of the call stack, you're using the heap now, which is much, much larger. Right? In fact, the vast majority of actual, recursive algorithms, they're not implemented recursively because it's expensive and it risks stack overflow. And so they'll simulate the recursion by using an in-memory stack. You can use backtracing optimization algorithms. For example, if you're trying to optimize something, you're trying to find the best solution, you formulate one solution, you go, okay, well, that's not feasible. All right, well, instead of starting over, what we'll do is we'll backtrack. If you add these 5 things, okay, now it's no longer feasible. Take off the last thing that you added and explore a different possibility. These are usually demonstrated using computation trees, right? And so you can backtrack through a tree, which is basically back to DFS, a graph traversal. The one that some of you might be aware of is the shunting yard algorithm. Have you ever heard of a shunting yard? I ask because a lot of people have family at UP.
Train,
Oh, there you go. There, exactly. What is the shunting yard in a train yard?
As I recall, is where like if you need to reorder a train, you can like store stuff, like store a line, break it into multiple smaller ones,
Yeah.
reassemble it.
How do you do that?
You need like a lot of just dead track essentially.
Right, so you
Shunt.
back this up into a shunt, right? And so you take, these cars go back there, then you sever one of these connections so that you can hook up a different one, right? And then move on. Well, guess what this thing here is right here? It's a stack, right? You're pushing it back into the stack so that, if there are cars 1, 2, and 3, and you need to pull them out, what order are they coming out in? 1, 2, 3, right? We put it in 3, 2, 1, but it comes out 1, 2, 3 because we backed it in, right? And that's a shunting yard algorithm for that particular algorithm is for that you'll experience in your lab in a couple of weeks for prefix notation on multiplication. So here, let me just show you. It's prefix. Is prefix? I forget what it's called. Anyway, 4 times 3 plus 1. Right. The order of operations here can be ambiguous, right? We know what they are because of PEMDAS, right? But it can be kind of ambiguous, but you have an alternative which is called prefix notation. So what you've got is, say, 4, 3, multiplication, 1 plus. What we're doing there is we're putting the operations at the front. So think about what this looks like, right? And how you could use a stack here to compute this. What you do is, well, actually, I'm not doing this exactly right, but I'm going to give you the idea of this. I wrote it in that direction for a reason. What we're going to do is we're going to work right to left, okay? And if we see a number, we're going to put it in the stack. We see another number, 3, we put it in the stack. Now we see an operation here. So what we're going to do is we're going to take the 2 numbers off the top of the stack here, and then we're going to apply that operation. 3 times 4 is 12, and then we put the result back onto the stack. We see another number, 1, and now we see another operator, plus. So we take those 2 numbers off the top of the stack, add them together, 13, and put that on the top of the stack. Have you ever seen an HP calculator? Or heard of an HP calculator? Like somebody going really, really fast on this stuff because they're using this notation, right? And it does not require any parentheses, right? It's completely unambiguous. And this is a prefix notation. Another name for it, thank you, reverse Polish notation or Polish notation, whatever it is. Where have you seen HP calculators like that?
My favorite chemistry professor used it.
All right, how old was he?
56.
Okay. Oh well, that's kind of young, right? So yeah, it's still a thing. It probably won't be a thing in the next 10, 20 years or so, right? It's kind of like the a slide rule, right? But you can get super, super fast, and you don't have to worry about any of this because there's no ambiguity. There's no need for parentheses. Pull out your phone, and what do you have to do? You have to type parentheses, and then go back, go back, go back, right? It slows you down. But if you use this prefix notation or postfix notation, reverse Polish notation, then you don't have to stop. You can get really, really fast at this stuff. Right? And there's a perfect use of a stack that you'll use in actually your lab. Right? We show you how to do this.
Oh.
No?
Oh, no.
No, don't worry about it. It's really easy. Right? We give you plenty of starter code. All right, what about queues? Where have you seen queues before?
You mean besides lines?
Besides physical lines. Buffers. Go to YouTube, and if you're watching this video right now, right? What happens on YouTube? It loads up a little bit of the data ahead of time so that you're not always constantly, pausing to load up more data, load up, the next 5 seconds or something like that. What is it called? Buffering, right? Where is that data stored? In a buffer. What is a buffer? It's a queue, right? Here's the next frame, here's the next frame, here's the next frame. Not exactly like that.
YouTube
Right?
videos aren't supposed to pause every 3 seconds?
Well, mine usually don't, right? Other than today, which I have no idea why it's not working, but buffers as queues. You can use server requests or what's called the consumer-producer pattern or producer-consumer scenario. For that, let me go ahead and pull up my iCloud here. I've got a picture of it from the book, my book. Where is it? Yeah, here's the producer-consumer pattern. So it really doesn't matter what you view these things as. These producers could be requests coming into a web server or something like that for a web page, right? Well, we can't serve them all at once because this is just a web server, right? It's got 16 processors, say. I mean, it can do a lot, but if you've got millions of people hitting this website at once, we need a way to manage all those requests. So we've got a bunch of producers here that are producing requests. We need to put them into a queue in the order that we receive them. Then we've got a bunch of independent consumers over here whose job it is to take this request and handle it. Right? This is exactly like you would have at a bank, right? We've got a bunch of tellers. We have a bunch of people. Now even this example or scenario is out of date because nobody does physical banking anymore, right? You just do it all online, right? But now the tellers are not physical people. There are just threads on a program or something like that, right? But producers produce these requests asynchronously. We need a way to store them, and that's called a blocking queue, right? And then these consumers, when they're ready to service a request, they come to the blocking queue and say, give me the next value, and I'll go ahead and take care of that and do this asynchronously, right? You want this to be what's called a blocking queue. Imagine that we don't have any producers at the moment. It's in the middle of the night. We're not getting any requests. But we've got a bunch of consumers that are ready to sit there and work and handle those requests. They keep going to the queue saying, do you got any work for me? Do you got any work for me? Do you got any work for me? Right? This is called busy polling. Right? Polling, remember, is asking the queue for the next thing, right? Because you poll the room. It's now serving number 38, right? But instead, there's nobody there. There's nobody in the room. Right? And so you keep yelling out, now serving, give me something to do, give me something to do, give me something to do. You're wasting resources doing that. That's busy polling. Instead, what a blocking queue will do, it'll say, all right, I don't have any work for you right now, go to sleep. That thread is put to sleep. It blocks and says, I will wake you up and let you know when I have work for you, so that we're not busy polling, wasting resources. Right? The second that a producer comes in, this blocking queue says, all right, great, I'll wake up one of these consumers that's waiting, give them the request, let them make the request, and then hand it off to them. You can also see that there's a delicate balance here. What if we have millions of producers, but only, say, 2 consumers? This queue will fill up very, very quickly, right? What if we've got thousands of consumers, but very few producers? We're wasting resources because this queue is almost always empty. We want to have some sort of a balance here, right? And this goes into queuing theory. Right? Have you ever heard of queuing theory from operations research or anything? Nope. So it's definitely not made up. You usually use a Poisson statistical distribution to estimate how many tellers you need at a bank or something like that. So queuing theory. Queuing theory calculator. You could calculate it online, right? So basically, you need to you come up with a model to simulate the system that you're trying to model, and then you try to find that balance, that steady state, where it's okay if we have a queue of size 10 on average. There are 10 requests waiting at any one point, right? That means that we've kind of balanced the number of consumers and the number of producers. Right? Because if somebody gets in your line and waits too long, you try to minimize their wait time, or you try to minimize the probability that they get out of line or something like that. Right? And that's a whole thing of operations research going back to the 40s or whatever. What is the history? I don't know if there's any history. Yeah, there we go. Going back about 100 years there. Right? And it's all under operations research. So if you ever have a choice of what math to take, I highly recommend combinatorics, operations research. Very, very useful. Otherwise, that's the producer-consumer pattern. You could also have what are called resource pools. This is something that we did not cover, at least in this section, but if you want to, you can watch my video from one of the honors section, where what we do, I speed up a bunch of database operations by doing it by using multi-threading, and to do that we use a resource pool. Right? What I mean by that is what we're going to do is we're going to have a queue of database connections, because the most expensive thing you can do with a database connection is that initial connection. So if you're always opening up a new connection and closing it, opening, closing, opening, closing, that's very, very expensive. Right? So what you do is you open 10 connections and you keep them open, but you've got to manage them. And the way that you manage them is by putting them into a blocking queue. Now, anytime that somebody one of your threads or one of your program needs a connection, it goes to this blocking queue and asks for one. If there are none available, then it blocks and says, wait until I have one available for you. You check it out like a book, and you use it as much as you want, but you don't close it. Instead, you put it back into the queue at the end of the queue, right? So that somebody else can use it.
So when would it be closed?
Whenever the program terminates,
Program shut down?
whenever the server shuts down, yeah. Because these are meant to be running 24/7 in perpetuity, right? Unless you need to take it down for maintenance or something like that. And even then, you don't, like big organizations, Netflix, we can't say, we're going to shut down Netflix for 4 hours to, for maintenance. Instead, you have redundant servers. We'll shut down that server for maintenance, but then all requests that go to it are rerouted to our backup server or something like that. And so it gets, that gets into system engineering that's even a higher level than this.
Oops, sorry, you can't use Netflix right now.
Right, well,
Can't use our order disc.
do they still do
Yeah, they
physical?
still do mail-in discs,
Okay.
apparently.
Well, we had it up until a couple of years ago, yeah, maybe 2 years ago. But yeah, I mean, there's still stuff that you can't get on streaming, or, you know, I don't want to pay for one streaming service for one show. I'll just go to Netflix and get the DVD or something. But that's resource pools or connection pools, right?
I don't know, they somehow managed to just invent cable again.
Yeah, we're right back at square one. I'm paying more now for all the services than I ever was for cable, right? All the subscriptions. Anyway, those are just some of the applications. You'll see them all over the place. Once you get used to using them, you start seeing them everywhere, right? Oh, this is a stack, this is a queue, right? Or use this data structure in conjunction with another data structure for this algorithm or whatever. Okay. That pretty much ends our list and list-based data structures module. What we'll do on next week, starting next week, is the next module, which is module 5, I think we're on, and that's going to be algorithms and algorithm analysis. So we've already seen a preview of this. We saw that, and in fact, I think I've still got it up here. We went through this exercise, right, where we observed that inserting at one end for a linked list was fast, but then inserting it, at least for our implementation, it was slow on the other end, whereas that was exactly reversed for an array-based list. What we'll do starting next Tuesday is we will look at this in a more formal, more mathematical and rigorous point of view. So we're going to come up with some math in order to capture this and then analyze functions, big O analysis and stuff. All right? All right, otherwise have a good weekend.